operate without electricity. In the 19th century, electrical energy was fairly well understood, but the technology that was needed to make it available for everyday use had not yet been developed. Today, all countries have access to some form of electrical power, and in a developing country like South Africa, electricity is essential for the further development of commerce and industry. In this video, Nonhlanhla Hlatshwayo is teaching a lesson at Ezakheni Secondary School near Ladysmith. The class is going to look at the fundamental principles governing the operation of simple electrical circuits and the common misconceptions that learners have about these principles. By the end of the lesson, learners should apply the relationship between current, resistance, and potential difference in a simple circuit. Experiment with the difference between connecting in series and in parallel. Be able to use a multimeter. Have participated in the scientific process of predicting, observing, and explaining. In the predict, observe, explain strategy, the teacher uses worksheets for the prediction phase. Learners use apparatus in groups for the observation phase, and group discussion takes place in the explanation phase.
Okay, class. What you have there is an activity with a number of diagrams. So what I want you to do, I want you to say whether a bulb will light up or not in each of those diagrams.
The activity sheet shows a series of diagrams depicting a variety of very simple circuits, some complete and some incomplete. The learners work through the activity sheet in 2s and 3s, deciding whether the bulb would light up or not in each case.
The second one is it is going to light up because there are two opposite charges.
The teacher moves from group to group, helping the groups function more effectively.
She's not satisfied. Explain to her.
Once the learners have worked through all the questions, the teacher takes a vote from each group on the answer to each question.
Now for A, I want all those groups who said yes, the bulb will light up to raise up their hands.
The diagrams which create a division of opinion show where there is confusion in the learners' minds. Essentially, what the learners have been involved in is predicting, the first phase in the predict, observe, explain cycle.
A typical experiment that learners or that teachers set up involves the predict, observe, explain experiments. It is referred to as POE. So learners first are given opportunity to predict the kinds of situations that occur, especially in the case of electricity or electrical circuits. The next thing they learn to observe and try to give an explanation of their observation.
So for each and every of those diagrams, you are going to connect the circuit and test whether your predictions were true.
The groups work through all the diagrams, making up the circuits as the diagrams indicate and testing whether the bulbs work.
It doesn't. So it's no. It's no. Oh man.
Write what you observe, not what you think it is.
No.
The learners record their observations alongside their original predictions. Where their observations contradict their predictions, it prompts them to consider why their predictions were wrong.
To tell me your observations now, what you observed when you were testing. Now for A, did the bulb light up? No.
The teacher works through the list of all their observations.
Now, can someone tell me why didn't the light bulb up in A?
Negative and positive charges meet at the same point.
Okay, I think that's current always from the
A number of recurring misconceptions are evident from the learners' incorrect predictions. Some have a unipolar model of a circuit.
In other words, there's no complete or closed circuit, just one wire used, and charges flow from the positive terminal of the battery or the negative terminal. So that's the unipolar model of the electric current.
Another misconception is that as long as the circuit is complete, the bulb will light up, even if it is not connected correctly as part of the circuit.
current must pass through the filament inside this glass. So for current to pass through the filament, it needs to go into the casing and then also into that lead contact or that nipple end.
In the next activity, each group is given a set of 4 or 5 identical bulbs to be connected in series in a circuit. They are then given a series of statements and have to decide which are true or false.
Before we connect the circuit, let us predict what will happen in each of those bulbs. Let us try to answer those questions. Then after that, we connect the circuit and we observe.
Among the statements are, bulb 1 is the brightest of the bulbs. All bulbs have the same brightness. The voltage or potential difference across bulb 1 is greater than across bulb 4.
Bulb 1 is brightest of all the bulbs. The thinnest bulb is 5. No, false. Why?
Because
All
they
bulbs
all
are
receive the same
because
current.
they are connected in series.
The first one.
The statements are designed to bring any misconceptions the learners may have into the open.
So you think the fifth bulb will be the brightest? Why do you think so?
Because the charge starts flowing into it before the charges get to the other bulbs.
The learners finish with their predictions and are ready to move on to the observation stage.
Number 4 is the brightest and number 1 is the dimmest.
Although the bulbs should all be identical and look equally bright, in reality they are not identical and have some flaws, so they vary in brightness.
Maybe our bulbs are not identical.
By swapping bulbs and eliminating faulty ones, the teacher manages to get all the bulbs in the circuits looking equally bright.
When you plug in, they are light the same. No one that is light brighter than the other one.
Why do they bend the same?
Because they receive the same current.
Now the learners have observed what really happens. Some are forced to change their views.
Is it true or false? It's false. So what is happening with the brightness of the bulbs?
The brightness of the bulb is the same.
If there's no link between the prediction and observation, if there's a clash, then learners need to be challenged in terms of a conceptual change. And then learners must be given opportunity to explain their answers.
Now, as I was going around the groups, what I found was that some of the learners or some of you thought bulb 1 will be the brightest because it is receiving electrons first, which is not the case.
This is known as a dissipative or consumption model of a circuit and is a common misconception.
They think that as the current is flowing, it gets used up. So they are using the dissipative model. They say the bulb which is connected to the positive terminal of the battery will receive the most current, and as the current flows to the other resistors, it gets smaller and smaller.
Another misconception is that the middle bulb will be the brightest. As it is here, the current from the positive terminal and the negative terminal will meet.
The other idea is the clashing model, where charges flow from both the positive end of the battery as well as the negative end. And when these charges meet a light bulb or a component in the circuit, they clash, and that causes the light bulb to light up.
In this activity, the learners make up a circuit consisting of 2 light bulbs and a variable resistor. What they are looking at is how varying the resistor's strength affects the brightness of the bulbs. Again, the learners will go through the process of predicting, observing, and explaining.
We are first going to predict what will happen if the resistance of the variable resistor is increased or decreased. What will happen to light bulb L1 or L2?
The learners first discuss the issue in their groups.
It will decrease. Increases. Okay. That's what I'm saying.
Okay, when the resistance R is increased, the brightness of lamp L1 will increase, decrease, remain the same. Yes?
It will stay the same because the resistor has been put after the lamp 1.
Okay,
L1 will increase.
will increase.
Yes.
Although the learner's answers still reflect the misconceptions of the dissipative model of a circuit, the teacher allows these to pass without comment at the prediction phase. The learners will be forced to rethink their views in the observation phase.
It's the current that will change.
So what I want you to do, because we do not have a variable resistor, we are going to increase the resistance of the resistor by increasing the length of this wire.
The learners find that as they increase the length of the wire and consequently increase the resistance, both bulbs get gradually dimmer.
It happens to the resistance of, to the brightness of L1 when the resistance R is increased.
The learners report back on their observations concerning the two bulbs.
Okay, if you increase the resistance of R, both L1 and L2 go dimmer. Is that what you are saying?
Yes. The teacher also picks up on the most common misconception of the learners, the dissipative model.
Some of you said if the resistance of R is increased, they said L1 remain the same. And they said L2 will decrease. They think that because L1 is connected to the positive terminal of the cell, it receives current first. And then when the current goes to R, all the current have passed here, so this one will not be affected, which is not the case.
In the final activity, the learners build the most complex circuit yet, with a bulb in parallel with a variable resistor, as well as another bulb in series. The teacher also introduces them to the use of the multimeter so that they can measure the potential difference across different points in the circuit.
It measures different things.
In the activity, learners can examine how increasing resistance affects current and potential difference in the circuit. Again, they use a varying length of wire as a variable resistor. The learners find that as the resistance increases, the brightness of the bulb connected in parallel increases, while the brightness of the bulb in series decreases. They also find that as the resistance increases, the potential difference across various points also changes.
As we increase the resistance...
The teacher rounds off the lesson by summing up the learners' findings.
So if we increase this R, V2 increases and V1 decreases. So now V1 and V2, they must always give you the value here because the sum must always be 6 volts.
We need to give learners an opportunity to talk about their ideas about electricity, their common sense ideas. And because these ideas are not are distinct ideas in the learner's mind, they could occur, there could be a multiple of different models in the minds of learners.
Hi everyone, we have just watched a video, and at the studio with me I have Dale, I have Andrew and Lolo. We are going to be talking about the lesson. The teacher in this lesson was concentrating on the misconceptions that learners bring into the classroom. Where do you think these misconceptions come from, Lolo?
With the background of the learners, when you take into consideration what is happening back home, they don't even have electricity. So they come with them, the misconceptions about electricity. They are not very, very sure about what is happening. So the teacher is fully aware of that, and she wants to eradicate that gradually by letting them voice out the misconceptions.
Mm-hmm. Anywhere else where the misconceptions come from?
I think, the dissipative model is a very common misconception, and it stretches across different cultures, so it's no respecter of cultures. So it seems like it's just there. It's perhaps got to do with the way people use language, which is different from how we use it in science. But there's a number of reasons. Another one that comes to mind immediately is sometimes, especially with regards to, sometimes this can come from us as teachers, as well, in how we approach the teaching of electricity. For example, The dissipative model, for example, I think if the teacher is not really established initially that the current is a flow of charge that comes from a potential difference, that you have a potential difference, and the potential difference, I mean, you know, you can use an analogy like a slope. If you have a slope, things will run down a slope. You have something running, current flow, you have a flow, because there is some difference there. You know, you need to establish the relationship between potential difference and current, and that current is dependent on the potential difference. And I think sometimes we don't deal with that sufficiently, and that creates misconceptions. I mean, for example, if you look sometimes at the graph that we plot, you know, I think sometimes the graph we plot when we do Ohm's law of V versus I, where you get a straight line and then you take the gradient of the line. The gradient of the line is V over I, which is R, which is correct. But the thing is, you've got I on the x-axis, which gives the impression that I is the independent variable.
Yes.
You see?
Yeah.
So it's so easy for learners to take something like that and for it to be totally conceptualized, established in them, and become a very serious misconception. And especially with regards to the fact that current is used up, you know, that sort of thing can come from there.
Are there any ways of correcting such misconceptions from teachers or learners in the classroom?
I think the predict, observe, explain method is an excellent way of dealing with things, because it provides learners with a discrepant event, something where they're expecting one thing to happen and something else happens. And that then challenges their ideas. They've got to stop and say, hang on, what I thought before is not working here. And unless you challenge those ideas, they're going to think that their common sense is actually good, and that all you're helping to do as a teacher is to take their common sense further. And they actually need something that contradicts their common sense. Because after all, that dissipated model is actually a very good common sense idea. Because we know that current is giving energy to the light bulb, and therefore that the current must be losing energy, and therefore you would expect the current to be slowing down. So it's a logical model.
The other thing that we observed in that video is that class was very big. It's a huge class. But the teacher managed to move around and facilitate the discussion in groups. How do you think that was done in this case? What are the things that you think the teacher did well?
The fact that she moved around the classes, the groups. Sorry, firstly she divided them into groups.
Yes.
And then she was moving around the groups to see that the groups are working efficiently, you know. And I think that's a very good thing, because if you've got a large class like that, you want everyone to be involved and engaged so that people can learn, you know. And one of the critical outcomes we have is people to develop actual skills of handling scientific equipment and so on. And so I think the fact that she went around actually helped us to circumvent the fact that she was dealing with a large class. And also, of course, the fact that, as I said, she had them in groups, she had them in small groups, which was very good.
I think it also helped that the lesson was really interesting to the learners, and she kept them busy. She moved from one activity to another, and that's a great help in dealing with a large class.
The worksheet was guiding them. So the pictures in the worksheet were also the apparatus that was brought into class. So they were able to look at the worksheet, compare with what is in their working board. So they were able to read the instruction from the worksheet, follow the instructions, and that makes the work for the teacher to be minimal.
She also overcame that handicap, if you like to call it that, by plotting down the different responses, you know, and making a tabulation of the different ideas that came forth. So she could capture misconceptions, you know, and so she could see also not only capture the individual misconceptions, but the extent of the misconceptions. And I think sometimes as educators, that's one thing that is neglected in my experience. I find that educators do not look at the extent to which the misconceptions are prevalent, especially in large classes, Tembi. It's very problematic. And she did that, used it very well, and engaged it to challenge those misconceptions. So I think it was good.
The teacher actually kept on saying which group, which is true and which is not true. And then the learners will say, this is true. And then the teacher kept on writing on the board. And then by doing that, I assume the teacher was trying to check on the predictions of
Yes.
the learners versus the observations. And I'm trying to ask, what do you think about the strategy that was used by the teacher?
Yes.
Do you think is it a valuable strategy to use in a big or large class?
Yes, I mean, as Dale mentioned that, you know, the discrepancy that you create, you have to create that. You actually design it, you know, so that the learners are challenged in that, wow, this is what I thought would happen. This is what looks like common sense. But this is what real experience tells us. So it challenges learners to reflect on their conceptions, and actually is a very powerful method of getting them to reject misconceptions actually and accept scientific conceptions. So I think she used it very well, and especially given that it was a large class, Tembi. She did it very well, and especially in those kind of settings, one needs to do that, because people can get away with misconceptions in huge groups. You know.
I also think it was important that she returned to their predictions when they had the observations, because it's too easy, oh, well, the teacher's given me the correct answer, now I'll throw away my original idea. And she got them to actually link the two up, and I thought that was good.
I think this is what we call in our terms dissonance, cognitive dissonance. So she did that specifically to create cognitive dissonance in order to establish the scientific. So I would agree with you, Dale.
And what do you think about the use of the chalkboard by the teacher? She had a summary there, and then at the end she had to pick up the ideas and the findings from the learners. How do you think the chalkboard was used, Lolo?
Again, I think the chalkboard was used efficiently and effectively, because all the learners were able to get the right predictions from the educator, the correct answers, correcting the misconceptions which were there.
Is there any other thing that you liked about this lesson?
I really liked the use of the practical apparatus. It's a very simple apparatus. It's something you could buy at a local hardware store, and it was used very, very effectively. And I actually think it's a lot more effective than some of the fancy circuit boards that you get, because there's not a whole lot of noise where you've got other bits and pieces, but you can see just what makes up the circuit. And the idea of using a long wire as a variable resistor was incredibly effective. Worked very nicely.
I think also from the other thing was, Tembi, when she was actually doing the experiment with the bulbs in series. I think one of the bulbs were faulty, so they were not quite getting the right result. And you know, that can throw a teacher off completely. But I think the lesson we should all learn is that when things do go wrong, and they often do in science lessons, you know, to allow learners to appreciate that fact and to investigate further. You know, she went and she checked the bulbs, and she tested them, and she got proper bulbs, you know, and then she got more or less what she wanted the learners to observe, you know. So that the one thing definitely we must be aware that sometimes experiments will not work, and this could be something just basically technical.
And it shouldn't be something that puts us off doing experiments.
Yes,
it's something you need to expect to happen, but it's still, experiments are still worth doing.
Yes, absolutely.
I think, thank you very much. I think that's all what we have today. Thanks, Dale. Thanks, Andrew. And thanks, Lolo. Thanks for watching. We'll see you next time, and bye-bye.